Thank you very much. Thanks for the invitation. And the hardcore group is still here. I also wanted to thank the other. Okay. I also wanted to thank the other speakers. Very informative, especially for somebody coming from the And so one of my goals, in fact, is to find out more potential cryptographic applications. So I'll talk about one very classical problem and a few others, but I'm interested in what else can we do with this machine. This is joint with Brett Hemingway and Nadia Imager here. And actually, it's a good thing. This is a great example of what you came about because Nadia gave us the working on 10. Let me explain the classical problem. I'm sure a lot of people know this well. 20 years ago, Coppersmith proved this now with the famous theorem that if you're given a big integer n, and you know some factor of p to within an error bounded by n to the quarter, then you can actually find that factor of that. And this was a the method which Coppersmith used was to say this, which and I'll go into more detail. If you're given some integer, that we might as well assume is bigger than n to the half, and we're told that there should be a factor of n that's within n to the quarter of that integer. What Coppersmith did was he used LLL to quickly produce a rational function that would have to have the factor you're looking for as a root. Now I'm going to talk about what the strengths were on this forces this mysterious factor to be a root of it. So what capacity theory is good for, and here I tried to about first initial Hedda, Sago, Cantor, we provide a kind of systematic way of producing these kind of auxiliary rational functions to satisfy the constraints that you pick out devices. And so one implication of this is actually a clean proof that in fact there are no rational functions of the kind that Coppersmith used to that would enable you to improve on that error estimate from n to the quarter to any n to the beta bigger than a quarter. The rational functions simply are not there. They don't exist. And so if you think about Coppersmith as a kind of an attack on a crypto system that hinges on having a factor of p, this is an attack on an attack. You can't do what Coppersmith did with you allow the error to be bigger. So let me talk about how you would use rational functions with special properties to constrain unknown factors of an integer when you have partial information. That's the nature of the game here. So we're given this large integer n and some approximation to a divisor of n. And what we're looking for now, I'm going to replace n to the quarter by an n to the epsilon. You're given an epsilon, and we're trying to find out if there is a factor p of n that is within n to the epsilon of p tilde. So let's just assume that our approximation is at least n to the half. And here's the constraint on rational functions that Coppersmith used. So z bar, I'm going to take that to be the ring of all algebraic integers. So we're trying to construct a rational function that has to have that p as a root if it exists. And his method was this. Okay. Right. So depending on what the epsilon is, I'm going to try to take some time to explain this. So you try to find a non-zero rational function which has the property that if you can factor n into capital P times capital Q, where these are any algebraic integers, then the value of your rational function on one of the either factor has to be also an algebraic integer. In other words, if you have, I'll talk about different ways of seeing those constraints, but another way to say this that's in fact equivalent is that this first condition is true if, let me write it down here, if for all primes L, if I look at the algebraic closure of Q, L, the L-like numbers, and if I take any number Z that's in here, so that what you could say is Z divides N in the integral closure of the L-adic integers, you want to force that to imply that this value is integral. Okay. So H could have denominators, but at least at numbers that are like this, where this is integral as well, I want this to happen. Now, for the number theorists in the audience, the kind of Z's that I'm talking about are simply the ones that have normalized L-adic absolute value between 1 and the absolute value of n. And so another way to think about this rather than this is that you're looking for a rational function which has the property that on certain subsets of the algebraic closure of QL, the L-adic absolute value of this is less than or equal to 1. Well, the other condition is Archimedean. Namely, you want this rational function to have Euclidean absolute value less than 1 on every real number that's within n to the epsilon of P. Tilde. P tilde was the approximation we had to the divisor. So you need to find such an auxiliary rational function quickly. And here's why this is enough to solve this factoring problem. If I had an honest divisor of n in the integers, and it was within n to the epsilon of this approximation P tilde, then you'd know two things. First of all, the value of the rational function on P would have to be an algebraic integer, but it's also a rational number. So then it's got to be an honest integer. But furthermore, because this P is in this interval that the second condition applies to, the absolute value H on the P is less than 1 in absolute value. So here you've got an integer that's less than 1 in absolute value. So it has to be 0. So the Coppersmith argument was about trying to find rational functions that have this property. So the first property I wrote there is kind of a slick way to write it, but the right way to think about it really is that on particular subsets of the algebraic closure of the L-adic numbers for every prime L, like this kind of annulus, I want the value of this function to be an L-adically integral. And this is saying on some subset of the real line, it's small in absolute value. So this is the kind of thing that capacity theory can do, can decide whether these functions exist. Okay, so this is, let me explain why epsilon equal to 1/4 is optimal. You cannot find that kind of rational function if I take n to the epsilon with epsilon bigger than 1/4. All we really need is this nice, beautiful paper of David Cantor from 1981. He dealt with capacity theory on the projective line. So what he proved was that if we take an epsilon and we're trying to find this auxiliary function of the type that I talked about, as long as you have integers that are at least some size that you can be very explicit about, if epsilon is less than a quarter, you can find this kind of rational function. They exist. And I'm going to talk about how he proved that existed. I should emphasize, though, that this is actually weaker than what Coppersmith needed. This is just an existence statement. The rational function exists. And the capacity theory community never really bothered to try to figure out how hard it is to find it. So that's another new thing to do. But if epsilon is bigger than quarter, there is no such rational function. You can actually prove it's not there. There's no way you can construct it. So this is sort of the trying to prove that this can't be done. And remember, this is when I take p tilde to be right in the middle. If I take p tilde to be the end of the half, and I'm looking for divisors that are within some bigger error, end of the epsilon with epsilon, the bigger the quarter within close to end of the half, you cannot find this auxiliary rational function that will have the boundedness properties on the previous slide. If, on the other hand, if you take a p tilde that's bigger than end of the half, something like end of the 3/4, then you can actually allow a bigger error. So if somebody tells you that you have a divisor that's around end of 3/4, then you can do a bit better. You can allow a tolerance of error less than 3/8. And what's amusing is that you sit down and work with Cantor's theory, and these numbers pop up.
Can you actually find H in the case?
Yes.
In case what?
Yeah. Yeah. We could do that. Yeah. That's what capacity theory is good for. See, this is the first step. You get an existence statement, but I want to talk about how to turn it into an LLL problem. Right? That's the other step. If you want to make this algorithmically quick, you have to go beyond what Cantor did. You have to do something. Yeah, that's what I'm saying. You can.
There's one thing I don't understand in your original theorem if P is really small.
Oh.
What happens in Coppersmith's theorem on the previous slide?
If the p tilde is really tiny?
Yeah, if I take approximation equal to 0, then it seems. Oh no, the previous slide. Yeah, okay, so I tell you that there is a factor of giving n to the 1/4 of 0. Then you cannot find p.
I think I need to know that the p is bigger than a end of the half for this to work. Yeah. In other words, if you are told an approximation bigger than end of the half with an error bounded by end of the quarter, then you can find it.
Otherwise, you have to test the relative errors?
Well, I suppose if you know a factor that's small, then you take n over p. Yeah. That's a good trick. Then you get something bigger than end of that.
Okay.
So I should have said that you need to assume that you're talking about factors that are bigger than end of that. Yes. 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 Yes, absolutely. The right way to think about it is that, let me get back over here. I think of it as like a magnifying glass. So you have this huge interval from 0 to n, and you pick a little subinterval in there, and you ask yourself, is there a factor of n in that subinterval? And the capacity theory gives you this magnifying glass to be able to look at that and quickly determine whether there's a divisor that's in that range. And it's a nice machine because you can literally put all kinds of constraints on the divisor. You could say, okay, it's in this Euclidean interval. Or you can say, well, it's in this larger Euclidean interval, but it satisfies a bunch of congruence conditions. Then the magnifying glass will tell you that too. So it's a very flexible machine for looking for divisors that satisfy particular combinations of constraints.
Is the algorithm deterministic?
Yes. I mean, it will say, yeah, it'll say this. Let me just get to this. It gives a nice answer. It gives a very sharp answer about whether or not these rational functions exist or don't. Okay, and you can ask, how many steps does it take to calculate the criterion? Okay, it may take a lot of steps to calculate it. Sometimes it's quick, sometimes it takes longer. The next question, though, as you're asking is it, suppose that the algorithm for existence says, yes, there is a rational function that does what you want. We'll magnify this set of constraints. How quickly can you find it? And that's a harder problem. And the difference between the two problems is kind of like the difference between saying some Minkowski argument guarantees there's a non-zero lattice point inside some large convex set. And the difference between that and finding a relatively short vector in the lattice. The convex symmetric set that you want to talk about has to be approximately an ellipsoid in order to be able to convert the Minkowski problem to finding a short vector. So I'm going to say a little bit more about that in a minute, but let me make sure I answered your question first.
May I ask
Yes.
another question?
Yeah.
Does it also find one prime that divide n in the same
Oh, yes.
interval?
Yes, it works for, doesn't depend on, P doesn't have to be, doesn't have to be.
So does it mean that it also implies an upper bound for how many divisors your n can have?
Oh yeah,
Okay.
I'll give that, I'll give that. It'll produce this rational function. Anything that's in that little interval that divides n has to be a divisor. Have to be a zero of each. I mean, let me talk about some other constraints, right, that you could put.
And each is really a rational function, not a polynomial.
It's generally a rational. It's a rational function. Yeah, it's going to be a rational function. In this particular case, in this example, when you're talking about constraints just lying in an interval, it'll be a Laurent polynomial in X. And the capacity theory tells you actually a lot about how to try to find it with LLL. Tells you a lot about how far down in negative powers of X and how far up in higher powers of X you need to go. So I was talking to Nadia about this, and we got to talking about, well, what other kind of conditions could you put on a factor of n? I mean, saying that you know it to within n to the quarter is saying you know the high digits. Evidently, it's well known that if you know the enough low digits, then you can also find this divisor. A really hard problem seems to be, suppose you know some high digits and some low digits, but you don't know middle digits. In principle, the capacity theory method would be able to tell you when you can construct a rational function that would pick out things that have a given set of high digits and a given set of low digits. But I don't know whether you can, I don't know whether the computations can be done in polynomial time.
But that is, I mean, still Archimedean and non-Archimedean information.
Yeah, yeah, right. Right.
It seems much harder if you're given the middle digits and not the outer.
Yeah, that's true. That's true. Both of those things are amenable to the method. I mean, so this raises a lot of interesting questions for the capacity people. How long does it take to actually compute the so-called sectional capacity? And given that, how long does it take to produce these functions? Okay, so I decided I would try to do a jargon-free cartoon of how capacity theory works, right? Because rather than from a cartoon, you can learn so much more from a really complicated technical discussion, right? So this is the cartoon, this is the best cartoon. And if I were really a cryptographer, I would have some designs up there, but I'm not good enough to do it. The cartoon works like this. Suppose we want to know if there is a polynomial with integer coefficients that has sup norm less than 1 on some interval on the real line. Okay? This is a cartoon version of what we have. Look at the real vector space of all polynomials with real coefficients that have some degree. And inside there, I've got a natural lattice. And now I can look at the set of polynomials with real coefficients that satisfy the sup norm condition. Right? So their sup values of x in the interval is less than 1. Now that is a convex symmetric set. Take a linear combination of two of these things with coefficients of x. So you have a nice convex symmetric set. And So you can say, well, if the volume of this thing is big, in comparison to the whole volume of the lattice, which is 1, then there has to be an and what capacity theory does is it provides you a machine to compute those kinds of volumes. There's a method of computing those systematically. And what's interesting is that the volume here, how should I say it? It grows like, well, the sectional capacity defines a constant that says how quickly this grows. But the growth of the volume tends to look like e to a constant times n squared. The n squared is important, because the n squared is what dominates over the dimension of this vector space. This is dimension n plus 1, and it turns out this volume is going to be growing like e to a constant times n squared, and it's whether the constant is, what the size of the constant is that matters. The constant positive or negative, it tells you what's going to win, because here you've just got a 2 to the n, okay? X e to a linear function of n. The volume will turn out to grow like e to a constant times n squared. Okay, so let me come back here. So if the volumes are growing like e to a positive constant times n squared, we're certainly going to win, and we're going to win pretty quickly, relatively small. On the other hand, it could be that the constant's negative, in which case you have no reason to think that the Minkowski argument could possibly produce a lattice point. But you might wonder, well, maybe it's there. It's just not going to be produced by Minkowski. And the deeper theorem here is that if the volume has an asymptotic growth rate that actually is small, e to a negative constant times n squared, then there really is no such polynomial. And that's a much harder theorem. And here's what they actually do. What they really produce in this case is that if the Minkowski argument fails, they actually produce infinitely many algebraic integers that have all their conjugates in this interval. Before I talk about how they do that, let's just imagine that we could do that. Imagine that you have this interval. You can find infinitely many algebraic integers that have all their conjugates in the interval. Now, if you had a function h that was actually a polynomial with integer coefficients that had sup norm less than 1 on the interval, evaluate it on one of these algebraic integers that has all those conjugates. Well, h on each of the conjugates then would have absolute value less than 1. So when you take the product of h over the conjugates, the absolute value of that is less than 1. But the product of h evaluated on the conjugates is just the norm of h of alpha, which is an algebraic integer. So h of alpha is an algebraic integer. Its norm, which is a rational integer, then has absolute value less than 1. That would mean h of that algebraic integer would have to be 0. But what they produced was infinitely many algebraic integers that have all their conjugates in this interval. So that proves that all of these algebraic integers would actually be zeros of h. And that doesn't happen, right? Rational functions don't have this. So the question is, how do they, if you have this situation where, in effect, the capacity is large, the volumes are growing very slowly, it's hard to make functions that have sup norm less than 1. What they do is they actually produce polynomials that have all their roots in this interval. And they do it first by constructing polynomials with real coefficients that are monic, that have all their zeros in a, b. And then there's a very delicate argument to correct the coefficients of a monic polynomial with real coefficients, so it becomes a monic polynomial with integer coefficients that has all of its roots. This is deeper than the Minkowski part of the theorem. And this kind of thing is only known. So what's the upshot here? This was the cartoon version of why capacity theory works. There's an easy Minkowski type calculation that says you're going to have a rational function of the right type if these volumes grow quickly. And if the volumes don't grow quickly, then you actually have a deeper theorem that says there are no such rational functions. Now Cantor and then later Bob Rumley developed this cartoon to treat rational functions on arbitrary algebraic curves over any global field. And what they looked at are, you have this curve over a global field. You start with some kind of curve over some global field. And what they looked for were functions that had these kinds of properties. If you take V as a place of K, meaning a prime ideal of the ring of integers or one of the embeddings of the R or C, you can talk about the algebraic closure of the completion and look at the points of this here. And what they looked for were, they chose subsets of the points over the algebraic closure of the completion on which you wanted to make sure that you constructed a function which had values. Well, it'll end up being a rational function. But this is a rational function. They wanted to make sure that for Z inside these domains, that when you evaluate, this is not so great. Sorry. They wanted to construct rational functions such that when you evaluate it on particular subsets of the v-adic points, you get something with v-adic absolute value less than 1. That just means that this thing is a v-adic integer. And for Archimedean places, you're talking about the points of the curve over the complex numbers, and you just put some subset of the points of the complex numbers, and you want your function to have absolute value actually less than 1 there. So their theory gives you, depending on how you choose these EVs, gives you a method of deciding whether there is a rational function that has this boundedness property in the v-adic sets and has poles in a particular set. So the classical case is the projected line. You insist that all the poles are at infinity, so you're talking about polynomials. And that's the classical case. Now, it turns out for the divisor problem, let me just say what the divisor problem is, how this sits in that context. Remember that we were trying to find p's that divide n so that p minus p tilde was less than or equal to n to the epsilon. So the kind of sets that you would take are these. You take the affine line over the algebraic closure of QV inside P1. And let's see if I can get this right. So when V, you want to pick a subset of the affine line. So I just identify this with QV1. If V is finite, what you pick is the set of points that satisfy that the absolute value of n at V is less than or equal to absolute value of Z at V less than or equal to 1. And as V is infinite, that's the infinite place of Q. You're just talking about E's that you just take the interval from P tilde minus n to the epsilon, P tilde to P tilde to the plus epsilon. And that's inside the points of the affine line over the reals. You pick those sets, and then you look for a function that's a rational function that turns out to have poles of f at 0 and infinity. What's interesting is you need, in Rumley's theory, the kind of rational functions that he's going to make are ones that all the poles are at 0 and infinity. And when you evaluate on any, for a finite prime, you look at any point here, the value of the function is going to be v-adically integral, absolute value less than 1. And over this interval on the real line, its absolute value is strictly less than 1. Now the subtle, no, I'm sticking, this is, I can take E to be a compact subset of the complex numbers. So this lives in R, but this, I think of that inside C, and C is the complex points. the subtlety in Rumley's theory and Cantor's theory really is that if you allow functions that have poles at several points, one subtlety is, well, I'm looking for this rational function that's going to crush these v-adic sets down into the v-adic unit disk and crush this interval down into the Archimedean unit disk. I'm allowing poles at, say, 0 and infinity in the classical case, in this case. Well, how many poles should it have at 0 and how many at infinity? And what Cantor's theory does is it uses game theory to predict how many poles it should have at 0 and how many at infinity. In fact, you should sometimes have more poles at 0 than at infinity, and in some cases more poles at infinity than at 0. It's kind of that's the interesting part of Cantor's theory. He sets up a certain game involving the places where you're going to have poles, and the outcome of the game predicts the best combination of poles to use to try to make this auxiliary function. And that's useful when you try to do LLL. Because in LLL, you need to write down a space of functions and then compute this volume within that space of functions of those that are v-adically bounded. And it's good to know what space to deal with. And the space you want to deal with turns out to be the meromorphic functions that have pole orders at 0 and infinity, for example, that have a given size. You let those sizes go off to infinity at a certain well-known rate. So that's actually another use of capacity theory in trying to do this. It tells you which spaces and lattices should you use to try to find these functions when you know they have to exist. Okay. So now the one thing I haven't said much about is exactly that last point. I mean, when you do this naive Minkowski argument and you find that the volumes of the convex symmetric subsets of functions that are v-adically bounded in a nice way, when those volumes are getting really big, you know there's got to be a so-called lattice point in there, which amounts to the rational function we want. But the question is, how do you use LLL to get that function? So let's go back to the cartoon. I believe in cartoon. So you go back to the cartoon. We were trying to find polynomials with supernorm less than 1 on an interval. If, by some miracle, the convex symmetric set of functions that have supernorm less than 1 turned out to be a sphere around the origin, we'd all know what to do. It's a sphere around the origin. We're trying to find a point in the sphere inside the lattice of polynomials with integer coefficients. So you just look for a lattice vector that's shortest. Right? The short lattice vector will do the job. In general, if you have some horrible convex symmetric set that's got lots of corners and angles and so on, there's no way to say that finding a lattice point in that convex symmetric set amounts to finding a short vector in the lattice. It could be a horrible thing. What you need to prove is that the convex symmetric set that you have to deal with looks more like a sphere, or relative to a set of axes, it looks like a sphere. It looks like a generalized ellipsoid. If it looks enough like an ellipsoid, you can convert the problem of finding this lattice point to finding this this lattice vector in the convex symmetric set to finding a short vector in the lattice. And that actually is a non-trivial step. In other words, there's that's a non-trivial statement about the types of constraints for which you can then use LLL to find the function that Minkowski predicts exists quickly. Let me just mention a few other problems. And so one of the things I want to know, things I want to ask people here is which other problems in cryptography revolve around finding auxiliary polynomials that have zeros that constrain the thing you're looking for. I'm very interested in that because I'd like to know what else can we use this for. Coppersmith also studied this problem, for example. If you take a monic polynomial of a given degree and you pick a large integer, suppose that you try to find all the solutions of a congruence, all integers solutions of a congruence which are small. In general, it's impossible to find all the solutions of this congruence that are less than n. I mean, I think you just take n to be the product of all the primes up to some huge bound, and you take the polynomial to be x squared minus 1. And you try to find all the things that are solutions of x squared minus 1, mod the product of all the primes up to some big bound. Too many solutions. But if you try to look for small solutions, then you can find them in polynomial time. and small was n to the 1 over d. And this is again done by constructing an auxiliary polynomial that has the property that if you have any integer less than n to the 1 over d, which is the solution of that congruence, it has to be an honest zero of the auxiliary polynomial. And again, the capacity theory predicts exactly why the n to the 1 over d is optimal. You cannot, if you try to increase n to the 1 over d to n to the epsilon with epsilon bigger 1 over d, there is no auxiliary polynomial that will do this in the same way. Another thing that Coppersmith looked at was this. Suppose you take a polynomial in 2 variables. Okay. What he was interested in was small solutions of f of xy equals 0. So what he did was he looked at the 2-variable polynomial. He looked at the coefficients, and he set bounds on how big x and y could be, which I'm going to call capital X and capital Y. And he said that you can find in polynomial time all integral solutions of fx0, y0 equals 0, such that the x0 and the y0 have these bounds, provided that the bounds that you've written down have this property that x minus y has to be less than or equal to this constant to the 3 over 2 times b. Well, that looks kind of peculiar, but that was the bound. Okay, so the point of this theorem was that you can find small integral points on curves quickly. And let me say that what capacity theory can do here. If you take a particular fxy, it defines a particular curve, and Rumley would tell you for which bounds on integral points, for which upper bounds on the absolute values of integral points, can you construct an auxiliary function which has to have the property that it vanishes at all integral points on the curve that satisfy those bounds. That's a computation, rather complicated computation in general for these curves. It's relevant to the factoring problem just because if you do this, I mean, you look at the curve in this case would be, if you fix n, you have a curve that's defined by just looking at x times y equals n. And we could be trying to find small points on that curve, or points that are near a particular real valued point. So if you want to find xy on this curve with x minus n over x minus p tilde and y minus n over p tilde small, that's the kind of thing that capacity theory on this curve is good for, and it's the same thing as trying to find actual divisors given an approximation to one of them. Okay, but what's amazing about this theorem is that he's not only working with a single curve, he's considering all curves that have that shape, and he's getting some uniform bound on the sectional capacity of the integral points that are bounded in an Archimedean sense, just as a function of the coordinates of the defining polynomial. So that's a direction we could try to go in. For a particular curve, we know exactly what to do, but when you consider families of curves described this way, that's a new thing to try. Okay, so I'm going to try to finish a little early, I think. Let me talk about what I think of as the future, and one cryptographic application that Nadia is explaining. So what we've been talking about is trying to construct rational functions on P1 or on a curve that have particular properties on points of the curve over algebraic closures of completions of Q. You want to find, and another way to think about these functions is they give you a a finite flat map to P1. Rational function on a curve is nothing other than that. It's a finite flat map to the projective line. And the kind of thing that we wanted this function to do was to take points on the curve over particular subsets of QV bar and push them down into small disks. So in higher dimensions, the natural thing to do is just to replace a curve by some variety of dimension m and replace P1 by projective space. Okay, so you'd like to look at finite flat maps from a higher dimensional variety to projective space, which have the property that if you look at this variety and look at its points over QV bar, you prescribe a particular set of points there, you want your finite map to crush that down into a small little ball. For almost all places, you need to be able to do that. Okay, let me talk about an application of being able to construct those things. There's this common GCD problem that I think cryptographers are much more familiar with than me. You're given some large integer n, and suppose we have a bunch of divisors. Somebody tells you there exist these divisors of n, which themselves have a large GCD. But I'm fudging them a little bit. I only know them up to some errors. So instead of knowing the divisors, I only know approximations to them where the errors are small. And what is interesting is then to try to see, okay, if the errors are really small, can you determine all those things? Given that the GCD of all these divisors is relatively large in comparison to n. And what Nadia has done is to do numerical experiments using multi-dimensional Coppersmith type methods. And she's got some results experimentally that say that the method works most of the time if the errors are relatively small in comparison to the size of the common GCD. But she tells me that the experiments usually work, but sometimes they just don't. And the question is, why? Is there an arithmetic explanation of this that has to do with the existence of finite flat maps? So now the next slide is rated MT13, I guess, a more number theoretic slide. So if you want to actually use capacity theory to do this, the variety you want is projective space. You take out the hyperplane of infinity, so you just have affine spaces. And now the natural generalization of what we did before, which is really the case of just having one divisor, was to take a subset of the affine spaces for each space B that consists of a little annulus around the point A1 through AN of bounded size. And at infinity, you do just look for R's that are bounded by an n to the epsilon, and that's the value at every place. So if you could construct a finite flat map from your projective space to projective space that crushed all of these things into the v-adic unit disk, and at infinity crushed into the open disk, it would turn out that the set of correction error things that you're looking for would then, because of the product formula, it would have to go to 0. It would have to be sent to 0 by this finite flat map. So all the solutions that you're looking for are in the fiber of the finite flat map from PM to PM lying over one point. And since it's a finite map, there's finite many points. So in principle, you could try to find it. But we don't know how to construct these. This is something that people in arithmetic geometry are really interested in these days. The Arakelov theory, for example, is really good at constructing one function. It's really good at constructing one function that has boundedness properties, but it's not really good at constructing a sequence of functions that would give you a map to a big projective space that would, push a set down. So Soulé, other people have been thinking about how to do this. The next stage in Arakelov theory should be, don't just construct single functions. Try to construct morphisms. Okay, so now I think I'll probably stop. So let me just finish with what the overall gist of this whole talk is, namely, anytime you've got some number theoretic cryptographic problem where you use an auxiliary function to constrain the solutions. because of boundedness in some sense, the auxiliary function. Capacity theory is useful. It should be useful for doing it. So it's a technique for finding whether or not they exist. Now, then the next stage is to try to show that you can find the auxiliary function quickly, and that's a harder problem, and there's a lot of interesting things to do. But what I'd really like to know at this point is from people in cryptography. But what other problems in cryptography have people used auxiliary polynomials to treat? That's really all I want to say. I have some X-rated slides that I can do. I'll suppress those. It's been a long week. Yeah. 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 Okay, so the question I'd like to know, for example, is this: suppose that you're Tom Cruise or something. I mean, and you've managed to get the secret code into your USB, but somehow you dropped it into the sink, and so you lost some digits in the middle, or you lost digits. So we know a p. There exists a p dividing n, and you look at the digits, but we're missing some digits. Okay, so the question is it interesting, for which combinations of digits is it interesting to try to figure out what p is if you know all but those digits? What Nadia told me was that if, for example, if you know the high digits, then you end up with coppersmith. Right? If we know the high digits, if we know these, and the low digits are unknown, then we have an OK type of theory. If you know the low digits, then I think you can, similarly, I think Coppersmith actually treated that. Right? If you know the low digits, but you don't know the high digits, then I think there's just a linear transformation that converts this into the previous one. And Coppersmith dealt with that. But I'm curious about what if you only know the bottom digits and the top digits, but the stuff in the middle is unknown. Capacity theory, I've been thinking a lot about this. Capacity theory would be able to tell you if there exists a rational function of the type desired that would pick out what you're looking for in this case. What I don't know, though, is whether you could actually carry out the calculations of these Green's matrices in polynomial time. I don't know. But I'm interested in whether this problem is of interest in cryptography. I mean, if you're missing the middle digits, does that? Well, this is just one that I thought of. I mean, for example, what crypto systems are built on finding small integral solutions of polynomials in two variables with integer coefficients? Is that something that people use? For example, Coppersmith's original paper dealt with how to quickly find integral points on affine curves defined by polynomials with integer coefficients. Is there a crypto system that's built on that difficulty? I don't know. Is that of interest, or is it mainly just something for number theorists to play with? What other cryptographic systems rely on trying to find, asking whether there exist points on curves, for example, which have either congruence conditions or Archimedean constraints? Yeah.
So what's the sort of arithmetic thing you would need in order to try to get a system like Coppersmith with small points on like surfaces? 3 dimensions.
Oh, 3 dimensions. Ooh. Well, the problem when you go up from curves is, again, the problem that capacity theory, which I was going to show you in the X-rated slides. Well, all right, I'll put up the X-rated slide. The X-rated version enables you to do this. It says you have some higher dimensional variety, like the surface that you're talking about. You identify some subsets of the points on the surface over QP bar, over the complex number. Can you find a single function that has absolute value less than 1 and all of those things? And capacity theory will enable you to find a single function. It'll enable you to tell whether one exists. It'll give a sufficient condition for finding it. There's conjectures that it's necessary and sufficient. But one function is usually not enough to constrain the solution that you're after. It would say that if you have this one function, it would say the solution you're looking for lives on the 0 set of that function. But if you're working on a surface, the 0 set of one function is going to be a curve. So you'd be able to say, well, the solution lives on this curve. Now, if you could find two independent functions, you could say the solution you're looking for lies on both of those curves, and then presumably that's something finite, and that's good. But that's kind of like constructing a finite map from your surface to P2, if you construct two independent functions. And Nadia has various hypotheses about the existence of such algebraically independent functions, is what she talks about.
So I mean, if you do run that, you have like a surface and you want a small integer point on it, you can sometimes find like a curve on which it lies, and then you have to find a small integer point on that curve. But that curve isn't giving you the plane curve, it's giving you as like an intersection of two surfaces. So,
well, yeah.
So this doesn't necessarily find you small integer points. Yeah, I guess, what if you wanted a small integer point that lied on the intersection of two surfaces? Like if you have some other model of an affine curve.
That would be good. Yeah, you could certainly do it. I mean, if you had two intersecting surfaces, the intersection is a curve. And if you could write down that curve, then Rumley's theory works really well. I mean, Rumley's theory is very powerful to give
even
you.
If it's not a plane curve.
Even if it's not a plane curve, it works absolutely generally. Of course, the computations are pretty hairy. But that was the amazing thing. I mean, Rumley's book, I think, is underappreciated. It was written in '89. Not very many people have realized what a powerful tool it could be. Right. Well, what would you need to make a decoder? What kind of thing do you need? I don't know enough about this, so I can't tell you. Oh, algebraic theory, algebraic numbers. So how do you construct the coding? How do you code? Oh, I see. Right. 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 Yes. Right. 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 Yes. 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 Right. Right. I see. Right. Yes. Well, that's certainly a good idea because, yeah, what this really comes down to, for example, you're trying to construct a big subspace of a linear system of divisors on a curve, for example, in the classic case you're talking about, that has various properties at certain points. Right? That's the standard case on curves. In higher dimensions, yeah, I mean, that's interesting. I know how to construct, I don't know whether I can construct lots of functions. That's a problem. I know I can construct one function using these kinds of volume ideas that has certain constraints. But trying to find lots of them, that's another question. But it might be. I mean, I have a feeling that that's related to the multidimensional problem. You're trying to find a. So what you're asking for is, if you take a surface, can you construct a good Kappa-style code relative to some, if you look at the linear system of functions on the surface that have poles no worse than some particular device, you want to find lots of functions that have poles no worse than that have some prescribed behavior. I think capacity theory does a little bit in that direction, but I don't know that it'll construct a big space. That's the question. Maybe if you can if you could eventually find nice maps from your surface to P2, then you could consider, pulling back linear systems from P2 via a nice finite flat map. That might be good. That's another reason to look for the higher dimensional stuff. That's a good idea. Yeah. Oh. Oh. I see. Yeah, that's interesting. Well, it might be, yeah, in other words, the thing you're looking for is the polynomial. Yeah. Well, that's a good idea. Good idea. Oh, okay. I mean, looking for polynomials is a lot like looking for integers if the polynomials have coefficients in a finite field, right? So in other words, what you're talking, let's take what you're talking about. You're looking for a particular polynomial over a finite field that has some special property. But if I could regard that as an integral point on some curve defined over a function field, and then you could use this technique to try to find it. I mean, that might actually, that's a good idea. That's a nice idea. I had never occurred to, that didn't occur. Yeah, when Nadia gave the colloquium where I first heard about this, she was talking about taking Coppersmith's theorems and changing Z to FQ of T. So there's a function field version. But the capacity theory works over global function fields as well as over numbers. Thank you. Yeah. Oh, okay. No, that would be very interesting because that sounds like the situation on curves. You have both P and Q, right? You know some bits on both P and Q. And P times Q is N. So the right thing to do would not be to work on P1, but it would be to work on that curve, x times y equals N. Look at the integral points on that curve that satisfy the constraints that you're talking about. And it'd be interesting to try to explain that. I'd love to know the reference. Oh, it's a paper of Nadia's. See, that's the trouble. I mean, she's done all this stuff, and I don't know about it. So, uh-huh. Okay. Thank you.